Hello, I am Jimmy Hu from Peking University. My paper is EH Task, Recognizing User Tasks from Eye and Head Movements in Immersive Virtual Reality. Let's start with the background of this work. Understanding human visual attention in VR is crucial for many important applications, including gaze cognition rendering, redirected working, layout optimization, VR content design, gaze guidance, as well as LOD management. However, previous works on visual attention analysis typically only explored one specific VR task and paid less attention to the differences between different tasks. Moreover, existing task recognition methods typically focused on 2D viewing conditions and only explored the effectiveness of human eye movements. Specifically, previous works have explored visual attention analysis for free viewing tasks in VR, visual attention analysis for visual search tasks in VR, task recognition for 2D images, as well as task recognition for 2D videos. Compared with prior works on visual attention analysis, we explore 4 different VR tasks using the same settings. We also analyze the differences between different VR tasks. Compared with previous works on task recognition, we focus on immersive VR instead of 2D images and or videos. We explore the effectiveness of both human eye movements and head movements rather than only human eye movements. Task recognition methods have many important applications in the area of virtual reality. They can be applied to adaptive virtual environment design, low-friction predictive interfaces, as well as attention-aware intelligent systems. Our contributions are listed below. First, we provide a new dataset that contains human eye and head movements and 4 task conditions. Furthermore, we analyze the patterns of human eye and head movements and review significant differences across different tasks. Finally, we present EH Task, a novel learning-based method to recognize user tasks in immersive virtual reality. We utilize the 360-degree VR videos as our stimuli. We ask participants to finish 4 tasks when viewing the videos. The tasks are free viewing, visual search, silence, and track. We collected the task categories, users' eye movements, and their head movements for further analysis. This table shows the statistical characteristics of human eye movements in the 4 tasks. For each item, the differences in the fonts of 2 tasks indicates that there exists a significant difference between them. We review significant differences in terms of mean fixation duration, fixation number per second, mean saccade duration, saccade number per second, mean saccade amplitude, as well as fixation distribution dispersion. We also analyzed the autocorrelations of human eye movements in the 4 tasks. We review significant differences in vertical direction. We also analyzed human head movements. We review significant differences in the aspects of mean absolute horizontal velocity, mean absolute vertical velocity, mean absolute horizontal acceleration, mean absolute vertical acceleration, as well as velocity distribution dispersion. We further analyzed eye-head coordination in the 4 tasks. We review significant differences in both the horizontal and vertical directions. This view shows the architecture of our model. We employed an EIH module to extract features from the eye-in-head gaze data. We employed a GIW module to extract features from the gaze-inward gaze data. We employed a head module to extract features from the head data. We applied 1D CAN and bidirectional GIU to extract features. We employed two fully connected layers to recognize user tasks. We evaluate the performance of our model on our dataset. We use both a cross-user setting and a cross-scene settings. We report the results of using a window and using majority voting. We find that our model outperforms other methods in both cross-user and cross-scene settings. We also evaluate our model in real-world situations. We find that our model outperforms other methods on a real-world dataset. We identify several limitations of our work. First, we only explored the 4 tasks that are mostly commonly used in VR applications. Second, we employed non-interactive VR videos instead of interactive 3D virtual environments as our stimuli. Finally, we mainly focused on the differences between different tasks rather than the differences between different stimuli. In the future work, we plan to overcome the limitations. We want to explore the effectiveness of other factors, such as human body movements and hand movements, in recognizing user tasks. We want to apply our model to other systems, such as driver system, AR system, and MR system. We plan to recognize other mental states in immersive VR, such as user cognitive loads and the levels of VR cyber signals from human eye and head movements. This is the end of my presentation. Thank you for your attention.